Once we have predicted the end behavior of a polynomial, whether it rises or falls on the left and right ends, then it's time to start examining interior behavior. Interior behavior consists of x-intercepts, maximums and minimums, and y-intercepts. In section 4.1.3, we'll discuss finding zeros by factoring. Now, a zero of a polynomial function is the solution to the equation p of x equals 0. So notice we have this word 0 here. 0 is the same thing as solution, and it is the solution when the equation equals 0. So we're setting our function equal to 0. The solutions to that equation are called zeros. These are the values of x where the polynomial equals 0. Now, if we set a function equal to 0, notice ultimately we're setting the y value equal to 0. On a graph, if y equals 0, then we're dealing with an x-intercept. So all zeros correspond to the x-intercepts of the graph. So technically, we're just learning a new vocabulary word. You know what an x-intercept is. You know to find an x-intercept by setting y equal to 0. Now we're just calling them zeros. By the way, your calculator will also call them zeros. Now, the difference between an x-intercept and a zero is simply notation. If k is a 0, that is, it is a solution to the polynomial set equal to 0, then the corresponding x-intercept is ordered pair k0. So k is the solution to the equation, but if I want to turn that into an x-intercept, I'm just recognizing that is an ordered pair location on the grid. Now, where did that come from? If x minus k is a factor of the polynomial p of x, then k is a 0 of the polynomial. You are already familiar with this concept as well. For example, when we solve quadratic equations by factoring, for example, something that looks like this, if we have a quadratic factored and equal to 0, my two factors there are x plus 1 and x minus 2. The 0 of that first factor is negative 1, and the 0 of the second factor is 2. So we're just making an observation here that when I take the factor x minus k and I set it equal to 0 and solve for x, I end up moving k to the other side of the equal sign. So where I see a minus in the factor, I get a positive in the 0. And again, you're familiar with that from your experience with quadratic equations. Now, we're going to be factoring polynomials which will have more than two factors like a quadratic. So we're going to be using several different factoring methods. So here are a few factoring reminders. When you begin factoring a polynomial, the first thing you always want to look for is a GCF. Remember, that is a greatest common factor. Get that out of the way first. Then observe the number of terms. If you have 3 terms, you can factor it like our traditional trinomials. However, if there are 4 terms, you may have to factor by grouping, and we'll review that in this section. If there are only 2 terms, a squared minus b squared, then it factors as a plus b, a minus b. So in example 2, we want to find all zeros to the following polynomial functions, and then officially express the x-intercepts as ordered pairs. So to find a 0, we set the function equal to 0, again, which means I'm looking for x-intercepts. Now, this polynomial only has 2 terms, but I'm going to start by factoring out the greatest common factor. Notice between the 2 and the 8, the greatest common factor is 2, and between x cubed and x, the greatest common factor is x. So we're extracting the greatest common factor to x. Now, when I take that out of each term, I should have 2 terms left behind. X squared minus 4. Now, double check by redistributing. 2x times x squared gives me 2x cubed, and 2x times negative 4 gives me negative 8x. So we know we have it factored correctly. Now, we are left behind with only 2 terms, and both of those terms are perfect squares. So we are looking at the difference of 2 squares. So we're going to apply this factoring formula. Now, I don't want to lose this little monomial term. I'm going to carry that along until I'm done factoring. X squared minus 4 factors as x plus 2 times x minus 2. So notice in this case, let's make some observations. We started out with a degree 3 polynomial. Remember, the degree is the highest exponent that I can find. And notice we ended up with 3 factors. There is definitely a connection there. Now, let's set each factor equal to 0 and solve for x, including that monomial GCF term. If I set that one equal to 0 and the other 2 factors equal to 0, that's going to give me 3 zeros total. Notice each of these is just a little linear equation. Dividing the first equation by 2, we get x equals 0. The second solution is x equals negative 2, and the third solution is 2. So we had a degree 3 polynomial. We got 3 factors, and notice we also ended up with 3 zeros. So the degree of the polynomial is related to the number of zeros and the number of x-intercepts. Now, we have found the zeros, but let's answer the entire question. Let's be thorough in our notation. The zeros that we found are 0, let me put them in numerical order. Not that it matters much. Negative 2, 0, and 2. Okay, those are the solutions to the equation. Now, to make it official, to put these as x-intercepts, we're going to write them as ordered pairs. That is negative 2, 0, 0, 0, and 2, 0. So in the case of this degree 3 polynomial, we found 3 factors, which meant we had 3 zeros, and those zeros correspond to 3 x-intercepts. I could certainly verify that with my calculator by graphing the function and observing that it crosses the x-axis at those 3 points. Okay, let's find the zeros for example B. To find the zeros, we set the entire polynomial function equal to 0. Again, observe that means we're setting y equal to 0, so we're finding an x-intercept. I'm going to start by extracting a greatest common factor if there is one, and in this case, there is an x, that's the GCF. So dividing each term by x, we're left with 2x squared plus 7x plus 3. This result is a basic trinomial, and that trinomial will break down into 2 binomials. Now, don't lose that GCF, carry it all the way to the end of the problem. Now, we're going to factor this trinomial using our traditional methods. Looks like it would be 2x plus 1, x plus 3. You can use any method that you feel comfortable with to factor that. But notice what our situation is here. We started with a degree 3 polynomial. Did you notice we have 3 factors? One of them's little and cute, but it is still a factor. So we will set all 3 of those factors, including that little monomial factor, equal to 0. Now, that one gave me an automatic solution. Not going to have to do anything further to that one. So one of our zeros is 0. Now, solving for x in the other 2 cases, we end up with negative 1/2 and negative 3. So this degree 3 polynomial has 3 zeros. I'm going to put them in order least to greatest because that helps me when I graph. But remember, you can put these in any order. Negative 3, negative 1/2, and 0. I like them ordered from left to right. Now, those 3 zeros correspond to 3 x-intercepts. Each 0 gets paired with a y value of 0 to make it an official location in the coordinate plane. So again, we had a degree 3 polynomial. We had 3 factors. We had 3 zeros, which meant we had 3 x-intercepts. So remember that leading power function not only tells me end behavior, but now it's helping me to predict how many zeros. All right, let's practice again. Example C, the goal is still to find the zeros. So the first step is to set the function equal to 0 and solve for x. We want to solve by factoring. The first thing we look for when factoring is a greatest common factor, and in this case, we do not have a greatest common factor between all 4 terms. Now, the fact that there are 4 terms gives me a clue that I should factor this by grouping. So let's talk about how to do that. What I'm going to do is group these 2 terms together and identify their greatest common factor. And I'm going to group these 2 terms together and identify their greatest common factor. So even though all 4 terms don't have something in common, we can pair them up 2 and 2 and begin factoring it. So between the first 2 terms, the greatest common factor is x. When I factor it only out of those first 2 terms, that leaves behind x squared plus 1. Now, looking at the second 2 terms, what do those 2 have in common? Their GCF is 5. So I'm going to factor a 5 out of those 2 terms, and that leaves behind x squared minus 1. Now, what's left is actually 2 terms. Here's my first term, and here's my second term. We know that they're terms because they are connected by multiplication, right? So each term has a couple of factors. Now, the goal in factoring by grouping is to make sure those second 2 binomials match, because ultimately we have 2 terms with a GCF. Just as we pulled the greatest common factor of these 2 terms to the left and the greatest common factor of these 2 terms to the left, we're going to take the greatest common factor of our 2 remaining terms. It happens to be a binomial GCF, but it works the same way. And I'm going to see what remains. Now, if I were in person, if you could see me, I am covering up with my finger the x squared minus 1s in both of those terms. And when we do that, we can see that x plus 5 is the result. So we are on our way factoring here, but notice I've got 2 terms here. Each is a perfect square, so that is the difference of 2 squares, and it factors as x plus 1 times x minus 1, and I still have this x plus 5. Now, you may have a question, how do I know when I'm done? When do I stop factoring? Well, remember, we were dealing with a degree 3 polynomial, and now we have 3 factors. So we want to keep factoring until each of those factors breaks down into a power of 1. We knew we could break this one down further because it was quadratic. Our goal is to factor it into 3 linear factors. That means x to the power of 1. Then we're going to set each factor equal to 0 and solve for x. And remember, this is just like solving a quadratic at this point. We just happen to have more than 2 factors, but it's the same concept. So our zeros for this polynomial in order from left to right would be -5, -1, and 1. And if we want to be official and write those as x-intercepts, that would be location -5, 0, -1, 0, and 1, 0. So our degree 3 polynomial ended up with 3 zeros, which meant 3 x-intercepts. And again, you could graph that with your calculator and observe that the graph should cross the x-axis in those 3 spots. So again, that one uses factoring by grouping. If you haven't seen that method before, that would be a good thing to research and practice. And you factor by grouping when you've got 4 terms. Example D, the problem is the same. Find the zeros. So we're going to set the function equal to 0 and solve for x. Now, these 3 terms have a greatest common factor of x cubed, so I'm going to start by factoring that out. That's going to leave behind a quadratic that breaks down into 2 binomials. This one would factor as x minus 2 times x minus 1. Now, I do have a degree 3 factor here, but I can't break it down any further. So I'm going to go ahead and set it equal to 0, as well as the other two factors, and begin solving for x. Now, to solve x cubed equals 0, we're going to take the cube root of both sides, and the cube root of 0 is 0. So we get x equals 0, x equals 2, and x equals 1. So for this problem, our zeros are 0, 1, and 2. The curly braces there just indicate a set. And our x-intercepts are ordered pairs 0, 0, 1, 0, and 2, 0. Now, did you notice something different about this problem? What was the degree of our original polynomial? This is a degree 5 polynomial, right? And how many zeros did we get? We got 3 zeros and 3 x-intercepts. We didn't get 5, okay? 5 is the maximum number of zeros that I can obtain. Any polynomial of degree n is going to have either exactly n or less than that as far as zeros or x-intercepts go. Okay, we have something going on right here called multiplicity, and we will address that in another video. Let's do one more example where we have to factor by grouping. So to find the zeros, we set the polynomial equal to 0 and solve for x. Now, a quick glance across all 4 of these terms, we would notice these actually do have a greatest common factor. So let's factor out an x. That's going to leave behind x cubed minus 3x squared minus 4x plus 12. Okay, so we took out a greatest common factor, and we've got 4 terms left behind. The 4 terms that are left behind, we are going to factor by grouping. So we're going to group these two together and extract the GCF, and we're going to group these two together and extract the GCF. But I don't want to forget about my little monomial out here, so I'm going to open up a set of brackets while I work on this degree 3 polynomial. The first 2 terms have an x squared in common. So if I factor that out just of the first 2 terms, that leaves behind an x minus 3. Now watch this. For the second 2 terms, the greatest common factor appears to be 4, but I'm going to actually take out a negative 4. Why? Because that would leave behind x minus 3. And remember, when we factor by grouping, we want those two to match. If I had taken out a positive 4, the second binomial would be negative x plus 3, and I would have a mismatch. Now, let's continue our factoring. Still working inside those brackets. Now looking at these 2 terms, they have an x minus 3 in common. So I'm going to factor that out. And just cover it up with your finger from both terms. You'll see an x squared minus 4 left behind. Not done yet. Notice that x squared minus 4 is the difference of 2 squares. So we're going to break that one down a little further as well. At this point, the brackets are redundant, so I can drop those. And the x squared minus 4 becomes x plus 2x minus 2. So reading the zeros out of each of our factors, out of our first little monomial factor, we get x equals 0. From the factor x minus 3, we get x equals 3. Also, x equals negative 2 and x equals 2. In this case, remember, we started with a degree 4 polynomial, and we ended up with exactly 4 zeros. Remember, 4 is the threshold number of possible zeros for this polynomial. So officially, the solution set contains values negative 2, 0, 2, and 3. And the x-intercepts then are negative 2, 0, 0, 0, 2, 0, and 3, 0, each of which we could verify with our calculator. In fact, let's do that very quickly. Let's graph our original function and type it in x to the 4th minus 3x to the 3rd minus 4x squared plus 12x. We'll take a quick peek at the graph, and I am observing the x-intercepts. Where does it cross the x-axis? There's negative 2, 0, 0, 0, 2, 0, and 3, 0. So very easy way to verify your calculations.